All right, let's talk about one of the most fundamental ways to bring order to data, bubble sort. You've probably heard of it. And you know, it's a classic for a really good reason. It's the perfect first step for understanding how computers can turn total chaos into clean, organized information.
I mean, think about it for a second. When you're faced with a giant, messy pile of anything, how do you even begin to sort through it? Well, usually, you do it the same way you'd tackle any big problem. You break it down. You take it one small, manageable step at a time. And that, right there, is the whole philosophy behind bubble sort.
So, why do we even care about sorting? Well, imagine trying to find a specific song in a massive playlist that's completely jumbled. Or what if your phone contacts weren't alphabetized? It would be a nightmare. You'd have to look at every single entry one by one. It's just incredibly slow. Sorting your data first makes finding what you need a million times faster.
Okay, before we dive in, let's just get one quick term out of the way. Array. It might sound technical, but don't worry. An array is just a programmer's word for a list of items, a container that holds a sequence of things together, like the numbers we're about to sort.
And this really shows you the payoff. With an unsorted list, you have no choice but to just check every single item. But with a sorted list, you can be so much smarter. You can jump directly to the right area where your item should be. It's literally the difference between wandering around aimlessly and using a map. So how does bubble sort do it? Well, its secret is a beautifully simple idea. Instead of trying to look at the whole messy list all at once, it narrows its focus way, way down. It only ever compares 2 items at a time, and specifically, 2 items that are right next to each other. That's it. That's the core mechanic.
Okay, let's see this in action. Here's our unsorted array. Bubble sort starts right at the beginning and looks at just that first pair of items, the 5 and the 1.
And it asks a very, very simple question. In this little pair, is the number on the left bigger than the number on the right? So is 5 greater than 1?
Well, yeah, of course it is. So the rule is just as simple. If they're in the wrong order, we swap them. And just like that, 1 and 5 trade places. See that? The array is already a tiny bit more organized. So, what's next? The algorithm just slides its focus over one spot to the right. Now it's looking at the new pair, 5 and 6. And we ask the exact same question all over again. Is the number on the left, 5, greater than the number on the right, 6?
Nope, it's not. 5 is smaller than 6, which means they're already in the correct order, at least relative to each other. When that happens, we do absolutely nothing. We just leave them as they are and move on to the next pair, 6 and 2.
Now, if we keep this process up, comparing and swapping all the way to the end of the list, something really cool happens. After just one full trip through the array, what we call one pass, the single largest number, in this case 6, has found its way to its correct final position at the very end. It has bubbled all the way to the top.
And this effect just keeps building. After the second pass, the next largest number, 5, bubbles up right next to the 6. After the third pass, the 4 finds its spot. You can literally watch as the sorted section at the end of the list gets bigger and bigger with every single pass.
Okay, this seems pretty straightforward, but it brings up a really important question. How does the algorithm know when it's finished? I mean, we can't just keep running passes forever, right? That would be, well, pretty inefficient.
In the absolute worst-case scenario, like a list that's perfectly backwards, we might need to make a pass for almost every item. So, for our list of 6 items, that could mean 5 passes. But running 5 passes every single time, even for a list that was already sorted to begin with, that just feels wasteful.
And this leads us to a really brilliant but simple optimization. Just think about it. If we go through an entire pass from beginning to end and we don't have to make a single swap, what does that tell us? It means every single pair we looked at was already in the right order. The array must be sorted. We can just stop.
And just look at the power of that one little tweak. In the best possible case, a list that's already sorted, our smarter bubble sort only needs one single pass just to confirm that no swaps are needed, and then it stops. That's a huge improvement.
So let's do a quick recap. Bubble sort works by comparing and swapping items that are right next to each other. With each full pass, the largest unsorted value bubbles its way to the end. And while it's one of the simplest algorithms to understand, it can be pretty slow on big lists. But, crucially, a smart version knows when to stop early if it completes a pass with 0 swaps.
And that leaves us with a final thought.
Bubble sort is this perfect example of a trade-off. Its logic is incredibly easy to understand and write, but for big problems, it's just not very fast. So it makes you wonder, right? When you're solving a problem, what do you value more? An idea that's beautifully simple or one that's more complex, but that's the job done a whole lot faster?